All right, today we're going to talk about something that is, no joke, the absolute bedrock of calculus, the limit. We're going to see how this really simple, almost obvious idea gets turned into one of the most powerful tools in all of math. So let's dive right in. So everything, and I mean everything in calculus, really boils down to this one question. I mean, we all get what it means for one thing to approach another, right? It just gets closer. But how do you make that idea mathematically solid, like totally airtight? How can you build a whole system of logic on a fuzzy word like approach? Well, that's the big puzzle we're going to solve.
Okay, so here's the good news. If you get the basic idea of approaching, you're already halfway there. You basically get what a limit is. It's just the formal, fancy language we use for that same intuitive concept. And this idea, it's the key that unlocks how we can formally define something as fundamental as the derivative.
And this really brings it all together. On one side, you've got the simple, intuitive df over dx, a tiny change in the output for a tiny change in the input. And on the other side, well, that's the formal definition. But look closely. It's not some completely alien thing. It's just spelling out exactly what the other side means. It takes that kind of vague, tiny change and calls it h. Then it says, hey, let's see what happens as h gets closer and closer to 0. See? The simple idea is just a shorthand for the more rigorous one.
And this right here, this is the whole point. The absolute genius of the limit is that it lets us deal with the idea of infinitely small without tying ourselves in logical knots. It's a total game changer. We don't have to worry about what an infinitesimal number is. Instead, we just focus on a process, the process of a normal everyday number getting smaller and smaller and smaller, approaching 0. It's so much cleaner.
Okay, so how did mathematicians finally nail down this idea of approach? How'd they make it totally rigorous with no wiggle room? Well, they came up with something that, I'll be honest, can look a little scary at first. It's called the epsilon-delta definition. But trust me, once you see how it works, it's actually incredibly clever. Let's break it down.
So let's just imagine a function, and this function has a little hole in it at some point. That means we can't actually plug in that exact value and get an answer. But look what happens as our input gets super close to that hole. See how the output from both the left and the right is zeroing in on one single value? That target value right there, that's the limit. Now, let's look at a different case. See this function? It doesn't have a hole. It has a jump, a total break in the graph. So as you come in from the right side, the output is heading toward one number. But if you come in from the left side, it's heading toward a completely different number. There's no single target that it's closing in on. And because of that, we have to say the limit here just doesn't exist. Simple as that. Okay, so this brings us to the formal definition, which is best understood as a game. Seriously, a two-player game. Here's how we play. I go first, and I challenge you. I pick an output tolerance. Think of it as a super tiny target window, called epsilon. And I can make this epsilon as ridiculously small as I want. Now it's your turn. Your job is to find an input tolerance, called delta, so that any input you pick inside your little delta window is guaranteed to land its output inside my tiny epsilon window. If you can always find a delta that works, no matter how insanely small I make my epsilon challenge, then you win. And that means the limit exists. It's just a foolproof way of proving that you can make the output as close as you want to the limit. Okay, I know that was some pretty heavy theory, but all that hard work, all that rigor, it really pays off. It gives us some incredibly powerful, practical tools. So now, let's see how that foundation lets us build a fantastic shortcut for solving really tricky limits. It's called L'Hopital's rule.
Okay, let's get our hands dirty with a real problem. We need to find the limit of this function as x gets closer and closer to 1. But there's a problem. If you just try to plug in 1, what do you get? Well, the top becomes sine of pi, which is 0. And the bottom becomes 1 minus 1, which is also 0. This 0 divided by 0 thing, it's what we call an indeterminate form. It basically means the answer isn't obvious, and we can't solve it just by plugging in the number.
So what are our options? Well, we could kind of cheat a little bit. We could just plug in a number that's really close to 1, like say 1.00001. If you punch that into a calculator, it spits out a number around negative 1.57. Now that's a really strong clue, but it's not a proof. It's just an approximation. We need a way to find the exact answer.
And this is where it all comes full circle. Remember how limits are the foundation for derivatives? Well, now the derivatives are going to come back and help us solve this tricky limit. It's awesome. The logic behind L'Hopital's rule is just beautiful,
And it all boils down to that core idea of what a derivative is. It's a way to approximate any curvy function with a simple straight line as long as you zoom in close enough.
So here's the key insight. For any smooth function, if you zoom in closer and closer to a single point, what happens? The curve starts to look flatter and flatter. It basically starts to look like a straight line. And what is that line? It's the tangent line. And the slope of that tangent line is, by definition, the derivative at that exact point.
So let's think about this. If we move just a tiny little bit away from our problem point, let's call that tiny nudge dx, we can approximate the function's new value. It's just going to be the slope, the derivative, times that little nudge. And we can do that for the function on the top and the function on the bottom. So the ratio of the two original functions is going to be pretty darn close to the ratio of their simple straight line approximations. And now for the magic trick. That little nudge, that dx term, it's on the top of the fraction and it's on the bottom of the fraction. So what can we do? We can just cancel them out. Gone.
And what are we left with? Something amazing. The limit of the ratio of the two functions is just the ratio of their derivatives. It's that simple. So let's try it on our problem. The derivative of the top part at x equals 1 is negative pi. The derivative of the bottom is just 2, so the limit is negative pi over 2. And guess what negative pi over 2 is? It's about negative 1.5707, exactly what our calculator guessed. This incredible shortcut, my friends, is L'Hopital's rule.
All right, let's just take a step back and look at the journey we've just been on. We started with this kind of fuzzy, intuitive feeling about what it means to approach something. We turned that into a rock-solid, rigorous definition, and then we used that solid foundation to build an incredibly powerful tool for actually solving problems. So, what should you really take away from all this? Well, first, limits are what make calculus rigorous and airtight. They're the language it's built on. Second, they're a super clever way to sidestep all the weird paradoxes of infinitesimals. Third, that epsilon-delta game we talked about, it might seem complicated, but it's the ultimate way to prove a limit actually exists. And finally, all this theory isn't just for show. It pays off with amazing practical shortcuts like L'Hopital's rule.
And that really brings us to a final thought. The derivative is just one big idea in math that kind of flirts with the concept of infinity. But think about integrals, right? Where you're summing up an infinite number of infinitely tiny slices. That's another one. And it's limits that give us the solid ground to stand on so we can make sense of these powerful, otherwise confusing ideas. It really makes you wonder, what other huge ideas out there that seem almost paradoxical could be made perfectly clear using this incredible tool?